Ignition sequence starts.
Good morning and welcome to Mission Control Houston. This is the International Space Station Flight Control Room, a place where a team of specialists is always on duty to keep tabs on the station, monitor its systems, and work with the crew members as they do science and take care of Earth's biggest outpost on orbit. And there'll be a big change on orbit coming up next week, but the preparations for that change did not keep the Expedition 59 crew members from taking care of business and breaking some new scientific ground.
Houston Station on Space to Ground.
Welcome to Space to Ground. I'm Kayla LaFrance. There were a lot of firsts happening on board the station. Canadian astronaut David St. Jacques took the station's newest robotic flyer, Astrobee, on its maiden voyage. Astrobee demonstrated its ability to navigate around the station while St. Jacques put it through its basic checkout activities, testing its mobility, cameras, and controls. Astrobee uses electric fans as a propulsion system to fly freely through the microgravity environment of the station. It uses cameras and sensors to help it see and navigate its surroundings. Robots such as Astrobee will play a significant part in NASA's mission to return to the moon, as they service future spacecraft and work to monitor and keep systems operating smoothly while crews are away. A nanosat is a miniaturized satellite no bigger than the size of a shoebox and weighing less than 10 kilograms, or 22 pounds. This week, the station crew released 4 of these cube-shaped satellites into low Earth orbit, each one representing a different country. The satellites came from Singapore, Japan, Sri Lanka, and Nepal. For Sri Lanka and Nepal, this was a monumental moment, for these nanosats were their first ever satellites to go into space, bringing both Sri Lanka and Nepal into the space era and offering new research opportunities for their scientists and engineers. This week's question comes from Stephen Brody, who asked if it is true that just about any area of study, psychology, research, medicine, can be a pathway to a space career. Thousands of people work for NASA. Of these people, a vast majority of them work in a wide variety of STEM fields, working on research in astronomy, geology, aviation, medicine, and space studies, just to name a few. However, not all NASA employees are scientists and engineers. NASA also offers opportunities for individuals with backgrounds in public relations, education, accounting, facility management, history, photography, and much more. The key is to find the career that you love and follow that passion, and it may lead you on a fulfilling space career. Keep sending your questions using the hashtag AskNASA. We'll see you next week.
When Space to Ground comes back next week, it will focus on a new expedition underway on orbit. Cosmonaut Alexei Ovchinin will be commanding Expedition 60, following the departure for Earth of Russia's Oleg Kononenko, NASA's Anne McClain, and Canada's David St. Jacques. That happens on Monday, June 24th. But the coverage on NASA TV and NASA.gov kicks off this Sunday at 2:35 p.m. Central Time for the ceremony marking Kononenko's handoff of station command to Ovchinin. On Monday the 24th, we'll be on at 2:30 p.m. Houston time to see the departing crew members enter their Soyuz spacecraft and close the hatch behind them. And at 6 in the evening Central Time, we'll start coverage of the Soyuz undocking from the International Space Station. That should happen at 6:25. Coverage resumes at 8:30 p.m. Central for the deorbit burn and will carry straight through the planned landing in Kazakhstan at 9:48 p.m. Our coverage will show you a lot of the highlights of a crew return to Earth, but we'll see it all from the outside of the Soyuz vehicle. What's it look like for the departing crew members as they leave their home on orbit to return to the home planet? Well, if you've got 60 seconds, here's an insider's view of what a trip to Earth on a Soyuz spacecraft looks like.
Welcome aboard the Soyuz MS spacecraft with non-stop service to Kazakhstan. Our flight time will be just under 3 hours 30 minutes. We'll be descending from an altitude of over 1,300,000 feet. At the time of departure, we're flying at a ground speed of 17,500 miles per hour. Please make sure all carry-on items are secured and that your seatbelt is correctly fastened. Now sit back, relax, and enjoy the flight. Ladies and gentlemen, we are now entering the upper levels of Earth's atmosphere. The estimated temperature outside is over 5,000 degrees Fahrenheit. During this zone of turbulence, we recommend you keep your seatbelt fastened while you're seated. As we start our final descent, our speed is down to 24 feet per second. At 1 second before touchdown, engines on the bottom of the vehicle will fire to soften the landing. On behalf of the entire crew, I'd like to thank you for flying with us. Welcome to Kazakhstan.
Although Kononenko, McLean, and Sinjak spent time this week preparing to come home, they did not neglect their science mission. This week, the crew wrapped up data gathering on the airway monitoring experiment, which examines an astronaut's exhaled breath for signs of inflammation. It's part of the process of designing future spaceships so that they are safer for their human crew members to use on long-duration missions.
The International Space Station is a national orbiting laboratory. Every single day we are answering big questions about Earth and about space, about where we came from and about where we're going. One category of those experiments are human research, experiments on our human body, how we react in microgravity. One of the recent ones that I've been a part of is called airway monitoring, and this is looking at airway inflammation up in space. So when we're breathing the air, you know, the small particles in the air, they don't just fall to the ground like dust on the ground. So we tend to inhale more fine particles than we would on Earth. And so we're looking at our response, our body's response to that by measuring nitric oxide exhalations as an indicator for airway inflammation. And so understanding, you know, how clean does our air need to be? How does our body react to the air? When we talk about going back to the moon, you know, a lot of people are aware that the moon dust is a very, very fine particle. It's almost like a powdered sugar fine particle. And if that's in the air and we're breathing that for months on end, if we're doing, you know, extended stays on the lunar surface, you know, we need to understand kind of how that affects the human body.
The International Space Station has several laboratory modules that house one-of-a-kind scientific research which takes advantage of the lack of gravity in space to test hypotheses in ways that can't be done on Earth. In the Destiny Laboratory, crew members use a special piece of equipment for experiments which involve potentially hazardous materials. And in the Kibo module, they are using a newer and bigger version of that glove box to support life sciences research.
Thinking inside the box. Presented by Science at NASA. Most people picture a glove box as the small space on the passenger side of your car. But if you're an astronaut floating 250 miles up, you might picture a large glass enclosure that allows you to conduct experiments that could change how we live both on and off Earth. This is the Microgravity Science Glove Box, or MSG. It was installed in the International Space Station, or ISS, in 2002 to allow small and medium-sized investigations from many disciplines, including biotechnology, combustion science, fluid physics, fundamental physics, and materials science. Many of these experiments can involve fluids, flames, particles, and fumes that you wouldn't want to escape into the space station's enclosed space, where they might make the astronauts sick or damage the station's sensitive computers and electrical systems. Instead, crew members install investigation hardware into the box and seal it shut. Next, they insert their hands into what's known as a glove ring assembly to safely manipulate their experiments or samples. Glove ring assemblies are available in a variety of configurations to accommodate differences in crew members' hand sizes as well as preferences in tactile response. The investigator views his or her work through an acrylic window. There's even the capability to install a high-definition camera system with a real-time video link installed inside the box to allow investigators on Earth to watch experiments being performed. The MSG has proven so popular over the past 16 years that a second glove box is being added to the station. The new model will focus exclusively on life sciences investigations and is known as the Life Sciences Glove Box, or LSG. This fully enclosed facility will allow crew members to perform developmental biology experiments on cells, insects, aquatics, plants, and animals. The LSG is almost twice the size of the original MSG and can accommodate 2 astronaut crew members, sometimes guided in real time by scientists back on Earth to conduct 1 or more experiments simultaneously. Safety was a paramount consideration in its design. As air circulates through the workspace, activated charcoal filters continuously clean it by absorbing chemicals that may be present. In addition, a high-efficiency air filter removes particles and aerosols. This allows the facility to provide 2 levels of containment for handling biohazard level 2 and lower biological materials. So why is it necessary to have a glove box on station devoted to life sciences? J. Michael Cole, the deputy manager of the ISS Projects Office at NASA's Marshall Space Flight Center in Huntsville, Alabama, explains. First, exploration crew members will be in microgravity conditions for an extended period of time, and it's important to note how that will affect their physiology and biology. The addition of LSG will supplement the ability to conduct those types of research experiments aboard the ISS. Second, life science experiments may give us new insights into how we treat diseases here on Earth. For instance, treatments for osteoporosis have benefited from research performed in microgravity. The next time you're asked to think outside the box, you may just want to consider one of the most unique labs ever built and think inside the box instead. For more inside information about what's happening inside the ISS, visit www.nasa.gov/ISS-science. For more on science happening on, around, and beyond our planet, go to science.nasa.gov.
For the astronauts, being the hands in hands-on science research is just a part of the job description. Astronauts and cosmonauts on the International Space Station also spend some of their time sharing the experience of being in space with us Earthlings. During the year of education on station, some of them worked on a series of STEMonstration videos to help students understand key scientific concepts, as Mark Vande Hei did when he focused on Newton's third law of motion.
Welcome to the International Space Station. I'm NASA astronaut Mark Vande Hei. Today, we're going to talk about Newton's third law. How do you think it will hold up in microgravity?
For every action, there is an equal and opposite reaction. This means that in every interaction between 2 objects, there are a pair of opposite forces acting on each object at the same time, a force pair. You can see that there are many examples on Earth. In space, thrusters expel one way and the vehicle is steered in the opposite way.
Hello again. More basketball stunts that I can't do on the ground, at least not while getting this much hang time. All right, back to serious business. Got a basketball right here. It's going to be object 1. I'm the second object. If object 2, myself, applies a force to object 1, then that same force will be applied according to Newton's third law by object 1 onto object 2. However, there's a big disparity in the mass. Object 1 is a very light mass object. Object 2, myself, is a larger mass object. So I'm going to try to make myself about the same shape as this ball. See how that works for us. And I'm going to apply that force. You saw that force applied to the ball made it accelerate quite a bit. It really didn't accelerate me much at all. Newton's third law again, but this time we're going to use two similarly massed objects. Joe and I have about the same mass, so Joe, get into a ball. I'll do the same. I'm going to face you this way so that I don't throw you into something you can't see. Now I'm going to get into a ball behind Joe, and I'm going to apply a force to him. Notice that when I applied a force to Joe, it accelerated Joe away from me, but I got accelerated away from him as well, because the force applied to Joe ended up being the same force that was applied to me. Now you've seen Newton's third law in space. Now test it out on Earth. See you next time.
The exterior of the International Space Station is a good spot for science, and commercial researchers and scientific researchers are using that real estate to capture digital imagery of Earth. MUSES, the Multiple User System for Earth Sensing Facility, is a platform on the outside of the space station that can hold 4 different payloads, ranging from high-resolution digital cameras to hyperspectral imagers, all of which will support several varieties of Earth science observations.
There's 4 places for 4 individual payloads to be mounted. These 4 places provide an individual scientist or a commercial endeavor to use this platform for acquiring access to spaceborne opportunities for looking at the Earth. MUSES is a multi-user system for Earth sensing. It's the first of its kind that actually allows the change-out of payloads on board this particular system. Robotic interaction with the onboard space station remote manipulator system actually allows plucking a payload off of this and replacing it with a new one. This is our server drawer. It's designed to take the volumes of data that we collect on board the MUSES externally and house that for temporary storage on board the U.S. laboratory for subsequent downlink to the ground. We actually have shoved 18 terabytes of data storage capacity in this single drawer that goes into the express rack. So one of its kind and first on board.
In order to support all future deep space exploration, scientists in NASA's Human Research Program have been trying to figure out what dangers such a long-duration spaceflight poses for the human explorers, and of course, then how to protect the crews who will be on those future missions. Some of that work is being done now on orbit. Some of it is also underway at the NASA Space Radiation Laboratory.
The NASA Space Radiation Laboratory is an outgrowth of Brookhaven National Laboratory's particle accelerator. It utilizes the heavy charged particle radiation beam from various components already existing at Brookhaven Lab to then deliver specific doses, ions, and energies of radiation to the actual NASA Space Radiation Lab itself, with the goal to determine the potential risks to human beings from exposure to radiation during space travel.
The bulk of the radiobiology data that we've collected from the NASA Space Radiation Research Laboratory has really helped us establish our space permissible exposure limits. NASA has a set of limits that helps protect the astronauts not only from the short-term effects of radiation, but also the long-term health effects. In order to establish what those limits should be, we have to understand how space radiation is different than terrestrial radiation. And the experiments at NSRL has helped us establish our permissible exposure limits in terms of protecting the crew from the risk of radiation carcinogenesis, and also setting non-cancer career limits to the brain for central nervous system effects, and also to the heart for cardiovascular disease.
The primary difference with trying to compare what type of radiation dose an astronaut would get on a mission to Mars versus what a person could expect in their day-to-day life over time is that time factor. Now, a mission to Mars, depending on when you go and how the planets are aligned and such, you're still looking at approximately a 2 to 3 year mission. And while that seems like a long time, it's very different than the amount of time that, say, a non-astronaut, just a regular person that has nothing to do with space travel gets over, say, a 70, 80-year lifespan from, say, some radon gas in the home, or from medical tests that are administered where you get a certain amount of dose from CT scans or PET scans and X-rays through the course of life. So you're delivering a certain amount of radiation dose in a more compressed period of time than you would to the person that has never been a space traveler and such. And that's one of the trickiest aspects to trying to determine radiation dose. The same amount of radiation dose delivered in a day is very different than that same dose delivered in 3 years, even though, well, it's the same dose. It's not that simple, and that has to be evaluated when you try to determine the potential risks of absorbing that kind of a dose.
The International Space Station's role in preparing for future exploration includes being a test bed for technologies that we'll need to make those trips. Things like the water recovery system that turns moisture from a number of sources into safe, clean drinking water. Here's how that works. Now, one other thing that we have already learned about supporting human beings in space on long-duration missions is that they have to exercise in order to fight off the negative effects of the weightless environment. Well, the International Space Station has been a proving ground for a number of systems that are designed to accomplish that goal. In this Speedy Time segment, astronaut Peggy Whitson gives us a rapid-fire display of a number of exercises that can be done with just one piece of equipment, the Advanced Resistive Exercise Device.
Today, we're going to talk about exercise in space. We have 3 different exercise devices here, and I'm going to talk about one of them. Of course, in zero gravity, we can't lift weights, so we have what's called a resistive exercise device. But it's got a really important feature. In order to protect the experiments that are going on board that might be sensitive to vibrations from us lifting this resistance, it's got a vibration isolation system that's actually very cool. As you move on the machine, it isolates any vibrations that we would have away from the structure and protects the science that's going on. And so we have to work out about 2 hours every day in order to maintain our bone and muscle mass. And this is my favorite, the ARED, the resistive exercise device. Squat. Sumo squat. Heel raises. Deadlift. RDL. Bench. Military press. Tricep extensions. Sit-ups. Curls. Forearm extensions. But you know what the best part about doing exercise in space is? The view.
If you would like to get another look at any of the stories we featured today, and who wouldn't, check us out on YouTube and Facebook. There are the addresses. And while you're at those spots, be sure to look around, because there is a lot of other cool stuff you can find in both places about NASA and America's human spaceflight program. And while you're out there bumping around on the interwebs, be sure to check out Houston, We Have a Podcast. That's folks here at NASA talking about their work in all aspects of space exploration. And today's episode makes a point. New episodes on Friday, and today we learn about NASA's crowdsourcing initiative and the new ideas that it's bringing into America's space agency. It's our talk with Lynn Bucquo and Steve Rader, who run that office from right here in Houston. Go to nasa.gov/podcasts for today's episode and all the previous episodes of Houston We Have a Podcast. Also at that location, the full library of all of the NASA podcasts, all of which you can also listen to on Apple Podcasts, Google Podcasts, and SoundCloud. This is Mission Control, Houston.